Hi everybody! So in today's video we are going to start talking about volumes by revolution, which is sort of what was demonstrated in class where we're revolving shapes and it creates a three-dimensional shape instead of slicing shapes up the way that we were last time. What you're going to want to have out, just so you know for today while you're taking notes, is you're going to want to have your calculator, you're going to want to have a straight edge, and you're going to want to have different colored pens or pencils out if that's something that you like to use, just so you're not scrambling in a few minutes to try to grab that stuff. So let's get started. So the first thing I want to review is how do we find the volume of a cylinder? The reason we want to review this is we're going to think about our shapes as being made up of very thin cylinders for the duration of this kind of process for revolving things. So the formula for finding the volume of a cylinder is volume equals pi r squared h. Now in this formula, the r represents the radius of the cylinder, and the h represents the height of the cylinder. So if you think about this flat kind of looking cylinder, almost like a hockey puck, the radius would be the distance from the center of the cylinder. You have to kind of imagine there's like a line through the middle. The center of the cylinder to the outer edge is the radius. And the height of the cylinder would be how tall each of these cylinders are. Sometimes we can find the volume of a three-dimensional shape by taking a curve and rotating it around a given axis. Now the axis we're going to use could be the x-axis, the y-axis, or a different line on the graph. There's just always some sort of line around which it's being rotated. To do this, we imagine dividing the solid figure into cylinders that have been turned on their side. So instead of our cylinders being oriented in this orientation, we're going to imagine our cylinders are oriented this way when we're trying to find these volumes. Which means the radius of the cylinders that we're going to be looking at will go vertically, and then the height would go horizontally. And this is what happens if the axis around which we are rotating is a horizontal line. If the axis around which we are rotating is a vertical line, the cylinders would still be oriented the way you see up here. Then what we imagine doing is finding the volume of each cylinder and adding all of those volumes together. The most efficient way to do this addition of adding up all these volumes is to use an integral, because integrals add things up for us. We call this method the disk method. And the reason we call it the disk method is that each individual cylinder looks like a thin disk, almost like a hockey puck or an air hockey puck, when you view it individually. So what process can you follow in order to be successful when you're trying to do these problems? The first thing you're always going to want to do is to sketch a very good graph. As we've seen throughout this unit, having an excellent visual of what you're trying to do is really helpful when setting up these problems. Then you're going to draw in the other half of your shape. So you'll notice this three-dimensional shape was created by rotating this two-dimensional shape. So when I say draw in the other half, what I mean is draw in the reflection of that shape, which is sort of this bottom half here, because it helps us to visualize how this would look three-dimensionally. Then you're going to want to draw in one cylinder to help you visualize the radius and the height of the cylinder. Identify the radius and the height of each cylinder. Then we would set up an integral that basically says add them all together. So your integral is going to say volume equals the integral from whatever bounds you have of pi times r squared times h, and then you would solve. So you're integrating the volume formula because you're adding up all of these volumes of cylinders. All right, let's go ahead and look at an example. So we're going to start with an example where we're going to use our calculator. It says the region between the graph of f of x equals 2 plus x cosine x and the x-axis between -2 and 2 is revolved around the x-axis to generate a solid. Some of the key vocabulary words you want to notice here is that we are revolving around the x-axis. As soon as you see the word revolved, you know that this is kind of a volume by revolution question. This is the type of process we're asking you to follow. The first step I would have here is to draw a really good picture. So I'm going to go ahead and set up my axes. Now it specifically says here in the question that the x values go from -2 to 2. So I'm going to go ahead and go like this and go like this. And now because I have a calculator, I'm going to use my calculator to create this graph. So I'm going to go to my y equals and I'm going to type in 2 plus x cosine x. I'm going to go to my window and make sure that my x min is -2 and my x max is +2 because I'm setting my interval so that it corresponds to the one provided in the question. And then I'm going to go ahead and look at my graph. It looks like my graph in this question looks like this. Now I don't need to be super precise here about the exact y values, but it looks like it kind of goes like this. Okay. Now this solid is created between here and the x-axis between -2, which is here, and +2, which is here. So I'm taking this region and I'm revolving it, and I'm going to use this idea of revolving. I'm going to show that on my graph by drawing a little spin around the x-axis. When I do that revolution, the bottom half of my shape would look like this, because it would be a reflection of the top half of my shape. And then what I like to do in order to visualize the solid that's created, this is three-dimensional, is you just kind of draw little ovals here at the ends. If you think about what this would look like visually, it's kind of like a flower vase that's been turned on its side. If I turn it this way, it might be more obvious. It's literally like a vase, but it's filled, it's solid. Okay. In order to find this volume, because I'm doing this using revolutions, I'm going to use the formula pi r squared h. Now, in order to be successful, I'm going to need to know what was my r and what was my h. So it looks like for each of these cylinders, which I can kind of visualize by looking at this circle, the r would be this distance right here. And it doesn't matter where you are in the picture, the r is the distance from the x-axis to the actual function, is the radius of your cylinder. So in order to figure out that distance, because this is a vertical distance, we would do top minus bottom. Or in other words, it would be 2 plus x cosine x minus 0, because the bottom is just the x-axis, which means I would just have 2 plus x cosine x. And if you want to kind of make a note, that's because I'm thinking top minus bottom to get that distance. Now the height of the cylinder would be very thin, but the height of the cylinder would be going the other direction. So in this picture, the height of the cylinder would be going this way. Now, to represent that very tiny change in the x direction, we call the height of the cylinder dx. So finally, I would set up my volume. This is kind of the before you do the work part, do this part. So my volume of my cylinder would be the integral starting from -2 and ending at +2 of pi times r squared times my dx. And my dx in this case is my h. Now my r we decided was 2 plus x cosine x. So here's your r squared, and here's your h. So you're just doing pi r squared h. You're just filling it in with the given information in the question. Because this is a calculator question, once I have this properly set up, I'm just going to go ahead and type this in. Pi, parentheses 2 plus x cosine x squared dx, and I would get 52.429. All right, let's try another problem, and this one we're going to do without a calculator. So find the volume of the solid by revolution generated when y equals negative x squared plus 4 and the x-axis over the interval from -1 to 1 is revolved around the x-axis. My first step here is going to be to draw a really good picture. Now I know that my interval only goes from -1 to 1, and I'm going to graph this function on that interval. So I know this should be a parabola, I know it should be an upside down parabola, and I know it should be shifted up 4 spaces. So I'm going to go ahead and draw that in. That means my parabola will start here, and then I will go over 1, down 1, over 1, down 1, and my parabola will look like this. Now I'm taking the region between -1 and +1, trapped between the parabola and the x-axis, and I'm revolving it. So I'm spinning this region of the graph. The reflected region, so the other half of this shape, would just be the same shape, but upside down because it's going to be below. It's going to be reflected. And then I can draw in little circles or ovals at the end to sort of help us visualize that this would be three-dimensional. All right, because it says this is the volume of the solid by revolution, by revolving it around the x-axis, I'm going to draw a little rotational symbol here to show I'm revolving around the x-axis. And I know I'm going to use the formula volume equals pi r squared h because each of these thin slices is going to be a very thin cylinder. In this case, we've got r and we've got h. Now my r this time would be the distance here. So my r would just be top minus bottom, which in this case would be -x squared plus 4 minus 0, which is -x squared plus 4. And again, I determined that by doing top minus bottom. My h, on the other hand, would be very thin slices going this way. And because those are moving in the x direction, my h would be dx, because dx just means a very small change in x. So my volume would be the integral from -1 to 1 of pi times my r squared times my dx. That's my h. And in this case, my r is -x squared plus 4. In order to do this integral by hand, what I would recommend is taking out the pi. So pi is a constant. I would move that to the outside of the integral because it's going to make it easier to evaluate the integral if I'm not dealing with evaluating things with pi until the very end. Now this right here really means -x squared plus 4 times -x squared plus 4. So in order to do this integral, I would multiply that out, and I would get x to the 4th minus 8x squared plus 16, and then I've got my dx. In order to evaluate this integral, I need to do the antiderivative. So my pi is still there, and the antiderivative would be 1/5 x to the 5th minus 8/3 x to the 3rd plus 16x plus c, and I'm going to evaluate that between -1 and 1. When I plug in the top number first, I get 1/5 minus 8/3 plus 16, and I know that the c's are going to cancel, so I'm not going to write that part, minus, I'm going to plug in my bottom number next, so I'm going to have -1/5 plus 8/3 minus 16. Now, rather than trying to simplify all of this separately from all of this and then combine them, I can see already that there are going to be some common fractions that have the same denominator here. So my process is going to be distribute this negative, which means this turns positive, this turns negative, and this turns positive. And I'm going to combine the things that already have a common denominator first. So I'm going to have pi times 1/5 plus 1/5 is 2/5. -8/3 minus another 8/3 is -16/3. And 16 plus 16 is 32. Once you actually combine those and add them together, which I'm going to do right now, let's see here, 2/5 minus 16/3 plus 32. The common denominator would be 15. I believe it's 406 over 15, and the pi would just get multiplied by that. So one of the ways we usually write this is 406 pi over 15. Okay, we have one more problem that I definitely want to do in this video because it is a little bit different than the ones we've already done. For problem number 3, find the volume of a solid generated when x equals -y² plus 1 and the x-axis between 0 and 1 is rotated around the y-axis. What makes this problem a little different than the first two that we did is that now we're going to be rotating around the y-axis. So it's going to look a little bit different, and we're going to have to approach it a little bit differently than we did before. Let's start with a really good picture. So our picture look like this. In order to graph this function, I would suggest making a table of values. Now, I know that it says that the y values should only go between 0 and 1, but to get a really good visual here, I'm going to have a few more y values in my table. So I'm going to have x and y. I'm going to choose y values. So I'm just going to go with -1, 0, and 1. Plug them into this equation. So if I plug in -1, I get -1 plus 1, which is 0. And then if I plug in 0, I get 1. And if I plug in 1, I get 0 again, which makes sense since this should be a parabolic function. And then let's graph those. So 0, -1, 1, 0, 0, 1, and here's my parabolic function. Now I'm only going to revolve the region between y equals 0 and y equals 1. So that would be this region right here. And I'm going to revolve that region around the y-axis. So you'll notice I'm drawing my little like rotational symbol in a different spot. If I revolve this region around the y-axis, the reflection of that region, the other half, would be over here. And if I draw in my little circle, it would look like this. So I can kind of visualize that. In order to do this problem, because we are revolving around the y-axis and everything is going from right to left, we're going to do everything in this problem with respect to y. We're still going to use the same volume formula as before. We still need to figure out our radius and our height, but it's just going to look a little bit different. Our radius this time will be this distance. So because the radius goes from left to right, we're going to do right minus left. So in other words, we're going to do negative y squared plus 1 minus 0, which is just negative y squared plus 1. And we got that by doing right minus left. Now my height of each of my cylinders would be a little tiny distance this way. So because it's a vertical little tiny distance, instead of a dx for a tiny change in x, we would use a dy for a tiny change in y. So my volume would be the integral from 0 to 1, because those are the y values here, of pi times my r squared times my h. In this case, my h is dy, and my r squared is negative y squared plus 1. Now, the actual arithmetic and stuff that you end up doing here is very similar to the previous example. So what I'm going to do is just go ahead and use my calculator, because we just worked through all of this arithmetic here, and this one ends up being very similar. You'll notice that the functions that are inside are very similar to each other. So you would have to write this twice, etc. Plug in your numbers. So if I just type this in on my calculator, I know this said no calculator, but we just did one without a calculator, so it's okay. We'd have pi parentheses negative x squared plus 1 squared dx, and we would end up with 1.676. All right, there are a couple more examples that we're going to try in class tomorrow before you get started. Thank you guys for watching and listening and taking really good notes, and I'll see you in class.